Don't want to make the latecomers suffer even more than they have to. I see them at the back. Why force them in the front? All right, homework 4 should be coming. Should be handed out now. I'll have it on the lab right after class. Any questions? We're doing graphs and trees and things of that sort. Okay. So remember we were talking about graphs? So you should recall what a graph is. I think at the very end we defined a subgraph. Right, a subgraph is just a subset of edges and nodes on the original graph. Tree, directed edge, weight, or maybe undirected edge, 8 degree, and we had in and out degree. Okay, so I'm just going to start throwing these terms around. So is there any term that someone doesn't remember? Okay. So, and remember we wrote W of E is the weight of edge E. Okay. We can write as a shorthand. The weight of a path P. Oh yes, a path. That's another term. Where P1, P2, dot, Pk with a piece of I are nodes. So WP, I think we said, is just going to be the sum from I equals 2 to K of W of P sub I. Let's do just directed. W of P sub I minus 1 comma P sub I. This could be the weights of all the edges on the path added together. Okay. And the weight of a graph let's say the weight of a subgraph. I mean, you apply the same logic to a graph. The weight of a subgraph S containing edges E1, E2, dot, E sub L is simply W of S is going to be the sum I equals 1 to L W E sub I. Right? Remember, we can use either notation for an edge, a pair of nodes, or just the edge itself. Okay, and we'll switch back and forth depending on what's more convenient. Okay, so now we're ready to move on. Or I guess this notation was new, but we're gonna talk about minimum spanning trees and shortest path trees. Okay, so this is MST, and this is SET. Not quite Stone Temple Pilots, but close. For those of you who are rock and roll fans. I see it in black and white. I don't know. It looks like I missed a spot shaving or something. It's the problem when they show you on video camera. I already showed you the trick on how to find where the camera is. All right. Won't go through that again. Okay. Let's talk about minimum spanning first. Okay. A minimum spanning tree of a graph Okay, so note I'm saying which means that there might be more than one of a graph G is a subgraph M that is a tree. I mean, it turns out we don't even need to make this statement, although it'll always happen to be true. Subgraph M that connects all nodes in G, so it's a connected subgraph. Okay, so our definition of tree assumes that it's a connected subgraph. Okay, it's a subgraph M that is a tree that connects all nodes in G. Okay, where the weight of M is less than or equal to the weight of S for any other connected subgraph S. Okay, so it's the lowest it's the cheapest set of edges that when you add them up together, they form a subgraph that connects all nodes. Okay. So why don't we do an example? Okay, so here's a graph G, and I want to find the set of edges that will connect all these nodes and also minimize the cost. So the cheapest graph in terms of the weight, the least cost subgraph, the least weight subgraph that will connect all nodes together. People get the idea? All right, so it turns out that we have to label all edges. Okay, in this graph, it's going to be that turns out to be the minimum spanning tree. So the thick edges, okay, let's say M be the subgraph of all nodes and thick edges. Okay, then the weight is what? 4 plus 2 is 6, 7, 8, 9, 10, 11, plus 3, 14, right? And you will find a cheaper graph to connect all those nodes together. Okay, so some of my nodes got sort of disappeared. There are the nodes. Okay, it contains all the nodes. Yeah, Faisal. A tree is a special type of graph. A tree is a graph that it's connected and has no cycles. Right, so you'll notice this subgraph that I happen to draw has no cycles. Oh yeah, another word in our vocabulary. Cycle. Okay? Let's define a shortest path tree before we go into the algorithms to build minimum spanning trees and shortest path trees. So a shortest path tree let's call it S. Well, let's say a shortest path tree rooted at node A. Okay, SA. So when we talk about a shortest path tree, we have to talk about the root of the tree. Okay, and what it means by root will be will become clear as we describe what a shortest path tree is. So a shortest path tree rooted at node A, S comma A. Excuse me. Has a path P sub j to each node, let's say node j. Oh, let's say to node nj. In the graph. Where the weight of pj is less than or equal to the weight of p for any other path from A to nj. Okay, so it's rooted at node A, and all we're saying is that there's this graph or this tree has some path from A to node nj, and that path, its weight or its length. Okay, so did I write? I just wrote weight. Okay, so we will also commonly refer to this as W of P, which is the weight of path P. We'll also call it length. I'm just going to start saying that instead. Okay, so the length of the path is just the sum of the edges on that path. It's synonymous with weight. Okay, so you find any path between node A and node nj, the path in the shortest path tree will be shorter, or no longer. Could have the same length. Okay, so let's see. Okay, so let's make this node over here the root of the tree we're interested in building. So I want to build shortest path tree from the perspective of this node here. And the shortest path tree is going to look and I should label all the edges. And we haven't affixed. There's a couple of nodes we haven't reached yet. 2, 3, 7, 6. Okay, I think this is the shortest path tree, rooted at that node. Okay, so for instance, there are several ways to get from this node to this node over here, right? But I claim that the shortest path will have length 1, 2, 3, 7. All right, and try to find a shorter path. I don't think you'll be able to. Okay, sometimes there are ties. So for instance, to get to this node over here, okay, I have a path of distance 7, 1, 2, 7. And you could have also gone that way and had distance 7. So again, the shortest path tree is not unique. But again, you won't find another path to get to any node that's shorter than the one that I chose, if I drew it correctly. So that's 8, 2, 3, 4, 5. Yeah. Okay. Okay. So you'll notice that there's a lot of possibilities. So just sort of randomly trying to find the right shortest path tree or minimum spanning tree is not easy to do. So there are algorithms to do it. And the algorithms turn out to be very simple. So we're going to look at those algorithms and look at why they work. Yeah, Patrick.
Exactly. Spanning tree and shortest path tree.
What's the difference between minimum spanning tree and shortest path tree? The difference is, I mean, they have different objectives. A lot of times it'll look very similar. But the goal of a minimum spanning tree is to minimize the cost of the sum of the weights in the tree. No notion of how far you got to go between nodes. So let me let me draw up the sort of the example that exemplifies the difference between the two. Let's see. Make sure I do this right. Yeah. Okay, here's a graph. What does a minimum spanning tree look like for this graph? Minimum spanning tree looks like this. Right? I got one node of weight 100 and all the other nodes are weight 1. You see it's a minimum spanning tree. There's no other way to connect this middle node to the other nodes without using an edge of weight 100. And obviously, I want to avoid using 2 of them if I can. So I use all the other edges of weight 1. Okay. And what is the shortest path tree? So let's call this middle node R. Shortest path tree at R. Looks like that. Right, distance 100 to every other node. Right? I want to minimize the distance or the length of the path or the weight of the path from that center node to all other nodes. And here the path has length 100. And you can't get a shorter path length than 100 from that middle node to other nodes. Right? If you take the minimum spanning tree, the path from this node to this node has length 100, but the path from this node to this node has length 101. Okay? People see the difference? I mean, this is an example that really exemplifies the difference between the two. So they're different objectives, and a lot of time the trees wind up looking very similar, but the objectives are not the exact same, and hence the trees aren't the exact same, and sometimes you can find examples where they're very different. Okay, any questions? Okay, so let's look at an algorithm to build the minimum spanning tree. And this is version 1. Because there's actually 2 versions of of the algorithm. I'm not going to be so formal about it when I don't have to be. So the algorithm is very simple. So it's do. Let me be a little bit formal. Why not? So we're going to build this graph. So M is going to be a set of nodes. It's going to start off as the empty set or set of edges. Okay. Find an edge, E dot in M. Okay, so E is not a member of M. No, let me say it this way. Let's call it Q, be the set of edges not in M, and whose addition to M does not create a cycle. In M. Choose E, or I guess, yeah. Choose an edge E in Q where weight of E is less than or equal to weight of E prime for any E. Okay, so a minimum weight edge in this set Q, and add E to M. Okay, and I should put a do here. Do this until Q is empty. And do it n minus 1 times, where n equals the number of nodes. Okay, so you just keep doing this process until any other edge you add is going to create cycles. And what we saw is that when you're building a tree has to have n minus 1 edges when there are n nodes in the graph. Right, so you're going to do this process n minus 1 times. If you're building a tree that's connected, we know we're going to do this process n minus 1 times. Okay? So if I go back to let's go back to this example over here. And we'll do the algorithm for that example. Draw the edges. Okay? So what do I always do? I always find an edge of minimum weight that hasn't already been added to the graph, which doesn't form cycles with the current graph. So currently I have nothing in the graph. So all I got to do is find minimum weight. So I can take any edge of weight 1 and add it to the graph. Okay. So I'll add this one first, and then I just keep repeating this process. I keep adding edges of weight 1 as long as they don't form cycles. And so none of these edges of weight 1, if I add them, do I form any cycles. Okay. Now I'm out of edge weight 1. So I'm still always picking the smallest weighted edge. So I got to go to weight 2. So I can add this one. This won't form a cycle. But adding this one will form a cycle. So I don't add that edge. That edge is no longer in my set Q. Okay? And so now I've got to go to edges of weight 3. That takes care of edges of weight 3. Edges of weight 4. This one will form a cycle, so I can add that one. I add this one. Okay? And by now I've connected all the nodes. Right? So there you go. Same graph. Right? Okay. So people get the algorithm? So why does the algorithm work? Okay, we're going to prove correctness by contradiction. Okay, so suppose the algorithm doesn't work. Well, before we get into that, before we get into the proof of correctness, in 1 minute. Okay, let me make a couple of claims, and you can help me prove these claims. So claim. The minimum spanning graph. So the least weight connected subgraph is a tree. What's the proof of that? And recall, I should also add, recall all edges, let's say non-negative weight. Oh, sorry, there isn't a unique one, so we'll say there exists a minimum. Minimum spanning graph that is a tree. How'd you prove this result? Yeah.
Trees don't have cycles. Cycle always has one redundant edge.
Right? Yeah.
So it has to be a tree.
Huh?
So it has to be a tree.
You're close. I mean, you got the right idea. So you're going to prove it by contradiction. Okay? So assume there is no tree. It is minimum weighted connected subgraph. Okay, it connects n nodes. So must have greater than or equal to n minus 1 edges right? Otherwise, there's no way to connect all the nodes. And if it had n minus 1 edges, it would be a tree. So it has greater than or equal to n edges. Right, and now you use your argument. This graph will contain a cycle, right? And so you can remove an edge in that cycle, and the graph will still be connected. So we should have said, sorry, by assume by contradiction, assume no tree is minimum connected subgraph. Let S be a minimum weighted subgraph with fewest edges. Sorry, so we needed that. So this S connects n nodes, so it must have greater than or equal to n minus 1 edges. N minus 1 edges is a tree. We said it's not a tree, so it has to have greater than or equal to n edges, which means that S contains a cycle. And we can remove an edge. This does not increase S's cost. Nor does it disconnect the graph. Can remove an edge in the cycle. Does not increase the cost, nor does it disconnect the graph. Okay, hence our contradiction. But because we chose S to be the graph with the minimum number of edges, that minimum number of edges that was a minimum weight subgraph. Okay, and if you took one that wasn't a tree, and we were able to remove an edge from it, which didn't increase the cost and was still connected, hence it couldn't have had the minimum number of edges. People follow that proof? Who gets it? Who doesn't get it? Or who needs more time to think about it? All right, let me go through it again more slowly. So the claim is that the minimum weighted subgraph is always going to be a tree, right? So we're going to prove this by contradiction. We'll say we have a graph that's got a minimum weighted subgraph, and none of the minimum weighted subgraphs are trees. Okay, so any minimum weighted subgraph is anything but a tree. Okay, so we're going to take one of these minimum weighted subgraphs, and the claim is that it can't have fewer edges than a tree, or it can't possibly be connected. This thing has to be connected. If it's not a tree, it's got to have cycles. If it's got a cycle, you can always remove an edge from a cycle, and the graph stays connected. Right? So you remove that edge. You're still left with a connected graph. The edges have non-negative weights. So by removing this edge, you've only decreased the cost. So you've got either a cheaper subgraph, or if the edge was of weight 0, a subgraph of the same cost with fewer edges. But we started out by choosing a minimum weight subgraph with the fewest number of edges. And we just found one with fewer edges and possibly lower cost, but it's still connected. So it's a contradiction. It's a good thing this thing fell and not the whole blackboard, right? Actually, I was in Los Angeles during the Northridge earthquake in '94, which was this big earthquake in LA. Which hit at like 4 in the morning on Martin Luther King Day. So almost nobody was at work. 4 a.m. and also a federal holiday, so the number of fatalities was drastically reduced. And I was a grad student, and when I came back to my office, there was this huge bookcase that had like crashed onto my desk. Like it decapitated me. So, it was. I viewed it as the Lord's sign that I should not work so hard. All right. Okay. That's just a joke. All right. So now the proof that that our algorithm gives the right to a spanning tree. Okay. So it's by contradiction. Okay. So let T, which equals let me go by T1, T2, dot, T sub n minus 1, be the edges, be the MST, or be the tree produced by our algorithm. Okay, where T1, T2, dot, 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 T sub n minus 1 are the edges listed in the order they were added. Okay, in other words, the weight of T sub j, I is less than or equal to the weight of T sub I plus 1, right? Because every time we add another edge, the weight of that edge cannot go down, because we're always adding the smallest edges that we can, the lowest weighted edges that we can that don't form cycles, right? So that's T. And let T prime, so we're assuming our algorithm didn't find the correct tree, let T prime be another tree where m is less than the weight of T. Okay, so we're saying our algorithm's wrong. We're going to try and prove it by contradiction. There must be some other tree. By that claim, the minimum weighted graph is going to be a tree. So we know it's a tree whose weight is less than the weight of our tree T. We're going to show that such a tree cannot exist. Okay. And let T prime be S1, S2, dot, dot, dot. S sub n minus 1 be the edges ordered by weight. So just like our tree, we're just going to have SI, the weight of SI less than or equal to the weight of SI plus 1. Okay. So let me before we go into the details, let me let's see. Okay. Actually, I need to do something a little bit stronger than the way I was setting this up. So I'm not going to abort this setup, but we're going to ignore t for a while, and we're really going to focus on t prime. So suppose, the problem with this algorithm is that we're not specific about which edge is picked next, right? Sometimes there's possible that there's a tie, and so it's hard to just focus on t because there are lots of other trees, or there may be other trees that are minimum spanning trees. So I'm going to focus on t prime now. And I'm going to have to say that we're going to have to say something a little bit strong about t prime. So suppose our algorithm. Oh, well, I guess I could say it this way. Yeah. Clearly, the algorithm not pick t prime. Right? Pick some t that's different than t prime. Okay, the algorithm did not pick t prime. Okay. And suppose no matter what order, what edges were chosen, t prime would not result. By the algorithm. Okay? What does that mean? There is some step when an edge is added to t prime. Oh, well, let's say it this way. There's some step in the algorithm where an edge would be added that is not in t prime. Right? And so suppose we had all edges in common. We run the alg and watch. Well, okay. So here's what I'm getting at. Yeah. Suppose we run the algorithm and build t prime. Okay, add edges in t prime until an added edge, until the next edge to add is not in t prime. Is this really how I want to do this? Yeah. So the next edge to add is not in t prime. Then when building t prime, add an edge not in t. Okay, so here's what I'm saying. So we have this graph. There's this graph T prime, which is the supposed minimum spanning tree, and the claim is that our algorithm cannot build T prime's minimum spanning tree. Okay, so what it's going to do is we're going to try and add edges. They're in T prime using the algorithm until at some point there's a divergence, and that the next edge that we want to add is not part of T prime. T prime has some other edge. Okay, so we can't add the edge to form T prime. So in other words, if you sort of look at this as a picture, graphically, visually. Okay, here's the graph, and there's some minimum spanning tree that's okay. There's T prime connecting all the edges, and what we're going to try and do is we're going to try and run our algorithm. And as long as the next edge we add is already part of T prime, we add it. And then at some point, we may want to add this other edge, and it's not part of T prime. Okay, and we can't just switch it for an edge of T prime. So what does that mean? It means that the edge we want to add doesn't form a cycle. The graph built so far, and has lower cost than the remaining edges to be added to T prime. Okay, so my algorithm says add this edge next. Okay, and or maybe there's a set of edges I can choose from that all have the same weight, don't form cycles. Okay, add one of those next, and none of those are in T prime. Okay, what does that mean? That means that T prime, all the remaining edges in T prime, I mean they're not going to form cycles either because T prime is a tree, but in addition, they've got to have bigger weight than these edges, because if these other edges in T prime had the same weight, then I would be allowed to choose from them as well. If they had greater weight, I mean that's okay. I'm saying if they had less weight, I would choose those other edges first. Okay, people see what I'm saying? That these edges that my algorithm wants to choose next. Okay, T prime doesn't include those edges. So every other edge in T prime must be larger than this next edge that I want to add. Okay? So now, so what? So I wanted to add this edge, okay? By adding it, because my algorithm wanted to add it, it would not yet form a cycle, right? So when T prime finishes being built, okay, at this point I can add it without making a cycle. T prime is going to complete its tree, and at that point it's going to be a connected graph, and it's not going to use this edge. So by drawing in this edge to T prime, I would form a cycle, right? And some of those edges in the cycle, they would have had to have been placed there after this in T prime, after we made this decision here. So those edges have to have greater weight than this edge. So let me try and write down what I've just said. Okay, so let's call them E1, E2, E sub k, the edges in T prime, and let's call this edge E. E is the edge I wanted to add. My algorithm would have added. Or an edge my algorithm would have added. Okay, and let these be the edges in T prime, which when combined with E form a cycle. Then the claim is that some edge E1 EK in the set satisfies weight of E sub I greater than E. Okay, if false, the conflict would have occurred sooner. Meaning, again, remember I'm adding edges until my graph, until T prime, I reach an edge that the algorithm can't possibly add. That's what I mean by the conflict. Okay? And when that conflict occurs, and I want to add this edge, okay, this edge cannot form a cycle in the graph. And so if I had already added all these other edges, E1 through EK, by the time I reach this conflict, I wouldn't want to be adding this edge. Okay, because it would form a cycle. Who's following what I'm talking about? All right. So if false, the conflict would have followed sooner. So now I'm gonna. So now I've got this edge E that has weight. Sorry, this should be weight of E. Okay, I've got this E that has weight less than this EI, and so now I'm going to modify T prime. Remove EI and add E. Okay, and it's still connected, still a tree. Okay, and it has lower weight. Okay, the weight dropped by E of, W of EI minus W. That's how much the weight dropped by. And that's contradicting. Okay, so let me try and sum up one more time, just to clarify. I want to prove that this algorithm gives me the minimum spanning tree. So we're going to prove it by contradiction. Assume it's false. Then there's some other tree T prime that has lower weight. Right? That's by the contradict. That's by the assumption that the algorithm doesn't work. There has to be some other T prime that wouldn't be generated by the algorithm that has lower weight. Okay, so now I have this tree T prime, and I'm going to run the algorithm, and I'm not going to worry about anything as long as there is an edge in T prime that my algorithm would let me add, right? So I start, I find the first set of first possible edges, the minimum weight edges that I could add. Let's say some of them are T prime. Well, if that's the case, then I can add them and I don't worry about it. And I keep doing that as long as the algorithm always gives me a set of edges that I can choose to add next. As long as there exists an edge that's in T prime, I add it. Okay. At some point, obviously, because the algorithm doesn't produce T prime, I'm going to run into a point in time where any of the edges I'm allowed to add, none of them are in T prime. Okay. So what does this mean at that point? It means that I want to add some edge. Okay, so that edge is not a part of the cycle on the tree we've constructed so far. Otherwise, I would want to add it. And that edge is not going to be a part of T prime. But in the final graph, when I look at T prime and I stick this edge in, I'm going to have a cycle. Right? So at this point in time, all those other edges that form the cycle are not yet there. Otherwise, as I'm building up my graph or building up T prime. Otherwise, I wouldn't want to add this edge yet. Right? So the edges in this cycle thing, but all the edges that I haven't yet added in T prime have to weigh more than this edge E that I want to add, because otherwise I would want to add one of those other edges that are in T prime that haven't yet been added. Or I could add one of those edges. So this edge is not added, and these other edges that are going to complete the cycle, some of them are going to weigh more. So when T prime is finally complete, the construction is finally completed, my claim is that if I add this edge E, I have this cycle where some of the edges weigh more than E, and I pull out one of those other edges, I've reduced the cost of T prime. I've reduced the total weight of T prime by swapping these two edges. Hence, T prime could not have been the minimum cost tree. Hence, my algorithm, it must wind up producing a tree that has lesser cost. Yeah, Ari.
Place the I by E until you get a tree that looks like one that the algorithm will spit out?
We're not really doing replacement. We're just trying to prove that our algorithm produces a minimum spanning tree. So to prove this, we say, assume there's some other tree that the algorithm cannot produce, T prime. And then what I show you is, well, look at T prime, and basically I'm finding an edge that I can swap into T prime and swap out another edge. That's a tree that has lower cost. That's a contradiction. And the whole point of this mechanism was to find this other edge. Well, the claim is the algorithm is wrong. So the algorithm produced a tree, and the claim is it's not a minimum spanning tree. Hence, there must be some T prime that has lower cost. And then we say, well, if there's this T prime, let's run our algorithm, and we'll add edges that are in T prime, and we'll keep running it until we get to a point where any edges we're allowed to add, they're not in T prime. And then you take one of those edges, and later on, when you're done constructing T prime, you can swap this edge in and pull out another edge in T prime that's more costly. Still have a tree, and hence you've reduced the cost. That's a contradiction. If you had the minimum spanning tree, you shouldn't be able to swap edges and reduce the cost. You shouldn't be able to reduce a tree that's even cheaper. Okay, hence the T prime cannot exist. Our algorithm must be able to generate a minimum cost tree. And there's also to prove it. So we've proven that the algorithm can generate a minimum cost tree. We'd want to prove that it can always generate a minimum cost tree. And to do that, you just have to show that no matter what order you add edges, the cost of the tree always winds up being the same. That's we'll skip that extension of the proof. But I just want people to get a general idea of how these proofs go. They can be pretty heavy and a lot of stuff to remember. I mean, in my notes, I did it a different way. Anyway, I have a slightly clean proof. I can send it around if people want. I mean, yeah, Faisal.
Get a new minimum spanning tree because a cycle would have existed. Is that a contradiction?
Cannot get a new minimum spanning tree because the cycle would have existed. No, you can't. Let me try and show this graphically, maybe. Okay, suppose here's my graph. Okay, and I generate. Suppose this is a minimum spanning tree. This is our T prime. Okay, and I can't get my algorithm to generate this thing. I mean, whenever I run my algorithm, it always generates a graph with higher cost. So now I got to prove that this T prime cannot exist. Okay? So I'm going to run the algorithm. And as long as the algorithm tells me, you know, there's a set of edges I can add next. You can add this one and you can add this one. Okay, so I got an edge in T prime that I can add. So I'll add that edge. And I'll go on to the next step. Maybe there's another edge in T prime that I can add. And now, suppose the next edge I can add according to the algorithm is this one. And it's not in T prime. Or it's this one, and none are in T prime. So I cannot add an edge and still be part of T prime. So what does that say about these edges that I can add? I mean, these are the, because my algorithm wants to add them, of the edges that are added so far, they're the lowest cost edges that don't form cycles. Okay? So all these are edges in T prime that could get added. They don't form cycles either. So you're not going to add cycles to T prime. So these other edges have to have higher cost than these two edges that I wanted to add. Okay? So now jump ahead to when you've drawn in the entire prime. Okay? Sorry. I need to have a connected graph. So this edge would have also been in T prime. Let's say, just so this node wasn't part of the tree. Okay? Jump ahead to the end. Now I've got this tree T prime. Okay? And these edges that I wanted to add were not part of T prime. Right? So if I add them, they're going to form a cycle. Right? They're going to form a cycle with some other edges that I added after I noticed this conflict. Those other edges have greater weight. So if I instead choose any of those edges with greater weight, you know, this one or this one, swap it out and put this one in. Okay, I've still got a tree whose cost I've reduced. I've put in an edge of some cost and taken out an edge of greater cost. Hence, I've reduced the cost. I've created a tree T double prime that's cheaper than T prime. You can't do that if T prime was a minimum spanning tree. That's a contradiction. Hence the algorithm must have constructed, or must have, it's possible to run the algorithm and wind up with a tree that's of minimum cost. And so T prime could have been generated by the algorithm, is the basic point. And now we just have to show that the algorithm always generates a tree of minimum cost, which would be another step. We'll skip it for now. I mean, it probably gets hairy. I'd rather go through the shortest path tree construction first. Okay. So there's a variant of the minimum spanning tree algorithm. A simple variant. So version 2. Restrict Q to edges that connect to the tree being formed. So I should say further restrict Q. Okay, so if you remember, the original algorithm said you can just add edges. You always want to add the minimum cost edge that doesn't cause a cycle. Right? That's what the first algorithm said. The only variant we're changing now is when you're going to add an edge, it's got to connect to this tree that we're already building. Okay, so if you remember, when I ran this algorithm here, right, I started, well, it's not a very good example. I mean, here, let me make a change here. Let's make this 2 and this 4. Okay, it's still the same cost tree, so it's still got to be the minimum spanning tree. When I ran the original algorithm, okay, I started and I could have added these edges in any arbitrary order, like so. You know, just started with all the minimum cost ones, and then next I would have jumped up to the next highest weight, which would be 2, and I would have added this one, and the graph is not connected. And the only other restriction we're making is whenever you're adding edges, it's got to stay connected. And of course, still no cycles. So in that case, you'll notice, I mean, the 1s all happen to be connected here, so we could have just drawn in all the 1s. Instead of adding 2 next, I would have added the 3, then the 4, right? Because it's connected to the tree that I'm building. And now finally, I could add the 2. And it turns out this doesn't change It changes the order in which you might add edges, but it also produces a minimum spanning tree. Okay, and a very similar proof by contradiction would work here as well. Okay. Okay, and now we're going to look at building a shortest path tree. Rooted at A. Okay, so initially, we'll call it S. S consists of A. Actually, yeah, let S consist of A. S will be the set of nodes. The set of nodes. And let's call it T. There'll be no edges. It's going to be the set of edges in our tree. Okay? And now, let Q be the set of nodes not in S, but who have an edge or from a node, I guess I really want to. In S. Okay? So Q is a set of nodes that aren't in S, but every node in Q is connected to a node that's in S by an edge. Oh, I'm going to need a distance measure also. Let's say D of A is 0. Okay? Okay, so now we're going to add node N to S. Well, let me do this. Let node N be Q. Okay, and mu1, mu2, mu_k be nodes that be nodes where this one I want to say is mu sub I is in S, and let E sub I be the edge mu sub I N. Okay? And let delta of N be the minimum over I of D of mu I plus way of EI. Okay, we're going to choose the n with the minimum delta n, add n to S, set d of n equal to delta of n, and add edge EI to T that satisfies and repeat. Okay, so what are we doing in this algorithm? It's probably easier if I just show you pictorially. Okay, so let's say this is the node. This will be the root of the shortest path tree we're trying to build. That's node A. Okay, and in D of A, D is always going to be the distance. So D of A is 0. Okay, and then what I do is I take the set of nodes that are connected by an edge to nodes that are currently in my set. So in this case, A is the only node that's currently in my set T. So these are the only two nodes that are currently connected to nodes in my set T, right? So then what I do is I find which one, when you take the node that they're attaching to, plus the distance to that node, whichever one minimizes that, that's the next node I'm going to add. So in this case, A is distance 0. Okay, so I'll draw a little 0 on top of A. And so this measure that I'm computing over here, up there, this delta of this node is going to be 1, 0 plus 1. The delta of this node is going to be 0 plus 2. Okay, so I add this node next, and its distance is 1. It's D. Okay? And, all right, so the number I'm drawing above is that node's distance D. Okay? Now, what nodes are touching nodes that are added to my set? Well, this node is touching A, and this node is touching the node I just added, and this node is touching the node I just added, right? And so again, I want to compute this distance delta for all these nodes. So this node has a distance delta of 10, right? It's this node has a distance of 1, plus the edge of 9 makes this node delta 10. This node has a delta of 2, and this node has a delta of 2. Okay, so I can add either one of them that has a delta of 2. So I'll add this guy next, and his distance is now 2. Okay, now my set T contains this node, and this node. Right? And again, I have to find this delta. So the delta for this node is 2. The delta for this node has 2 deltas. It can go through this edge, distance 1 plus distance 9 is distance 10, or through this edge, distance 2 plus distance 3 is distance 5. Okay, but this is the node I add next because it has distance 2. So this guy gets added. And now the set of nodes I need to consider are this one, and this one was already added. Right? And again, I have to compute all the deltas. This node has delta, this plus the D of 2 plus the distance 1 edge. Okay. This one has distance 7, 2 plus 5. This one has distance 7, 2 plus 5. This one has distance 5, 2 plus 3, or 10, 1 plus 9. So the minimum was 3. So this node gets added next with distance 3. And that's applying this algorithm that I showed over there. Okay? People get the algorithm? Again, you have a set of nodes that have already been added. You take those sets of nodes and you find nodes that they connect to that have not yet been added. And then you're trying to compute a possible distance for nodes that have not yet been added. And that distance is the minimum from any node that's been added plus an edge that's connecting them to that graph that you're building up. Okay, that's tentative distance. You always add the one with minimum distance and start the process over again. Okay? So we'll pick up next time from there. Did the homework ever show up? Ah, great. And was there another handout as well? There should have also been midterm solutions. Oh, they're stapled together. Okay.